Good afternoon. Test one is just around the corner, and if we look into just some of the remaining items regarding Chapter R, and then we're going to touch briefly upon functions, which will be formally introduced in Chapter 1. Okay, first things first. Okay, and going back to all types of equations, and we have from page 113. Okay, we have a radical equation that consists of two radical terms. Okay, the first of which we have the square root of k plus 7, and the next we have the negative of the square root of 3 minus k. And for these terms, okay, we have the difference between the square root of k plus 7 and the square root of 3 minus k is said to be equal to 2. And we want to determine, okay, just what the value of k is. And so for what we have in this setup, and I can isolate either of the radical terms. And whenever you're working with equations that consist of two radical terms of the same type, like where both of these in this case happen to be square roots, you want to isolate one of these, because if you square both sides, you're going to come out to like the square root of k plus 7 times 3 minus k, and you're starting out with a complex enough problem where if you're to do something such as square both sides, you'd be going from a complex problem to making something even more complicated. Like you mean to untie a knot, and then your approach could be, like I say, getting things tangled up even more. So just to make things as simple as possible, okay, if we isolate, let's say, the square root of k plus 7, okay, we can add the square root of 3 minus k to the opposite side. Okay, so and in doing this, okay, so left hand side, okay, we have with the square root of k plus 7 is equal to 2 plus the square root of 3 minus k, and with the square root of k plus 7 by itself. Okay, so we can square both sides, and again with two radical terms, you don't square both sides until at least one of the radical expressions is isolated. Okay, so for what we have here with the square root of k plus 7 squared, okay, so this will become k plus 7. And for what we have to the right, now we have the square of this expression. So you have 2 plus the square root of 3 minus k times itself. And if you were to envision foiling out, okay, like you have 2 times 2 is going to be at 4. And the outside and inside terms would each be at 2 times the square root of 3 minus k. And if I add it together, I would have 4 times the square root of 3 minus k. And the last product would be the square root of 3 minus k times itself, or like the square root of 3 minus k squared, and that would have 3 minus k freed up in this particular instance. And so for what we have to the right, okay, so we have constants to combine with 4 and 3, so we're going to have 7, and we still have a remaining radical term with 4 times the square root of 3 minus k, and we have negative k to follow. And for what we have at this point, we're going to have like terms to combine, and doing so we're going to isolate 4 times the square root of 3 minus k. So I can move, let's say, the k from the right over, and I can also move 7 by subtracting, and that's going to cancel the constant on the left and the right hand sides of this equation. Okay, so we got k plus k is going to make 2k, and we have is equal to 4 times the square root of 3 minus k. Alright, so for what we have now, I could go ahead and square both sides, and notice we have leading coefficients that are even. Now you could technically isolate the square root of 3 minus k upon dividing by 4, but you would have like 2/4 of k, which would be k halves, and so you would be looking at working with a fraction. And let's say that to avoid working with fractions, we just divide both sides of the equation by 2. Again, there's more than one pathway to create in following through. You could go ahead and square both sides, you could divide by 4, but I would say perhaps the simplest display would be just to divide by 2, where we would have k is equal to 2 times the square root of 3 minus k. Alright, and with the radical in the form of the square root of 3 minus k present, we can now square what we have here. So for what we have on the left, okay, we have k to the second, and with 2 times the square root of 3 minus k squared, we're going to have 2 squared is 4. The square root of 3 minus k squared is going to be 3 minus k. Now on the right we have squared the factors, but squaring out does not automatically take care of the multiplication that is required. Okay, so we have k squared, and now officially following through and multiplying. So the square of 2 times the square root of 3 minus k, this is going to translate to 12 minus 4k. And if you notice, we now have a quadratic equation, and we don't have this one in standard form yet, but I can make adjustments and set this equation to 0. So I have the highest order term with k squared, and I can just move the lower order terms by adding 4k and also by subtracting 12. Alright, so we have k squared plus 4k minus 12 is equal to 0. And from the standard form, it's going to be a trinomial that can be factored into integer coefficients. And with the factors of negative 12, that will have a sum or difference on the plus side of 4. We'll have more weight given to the addition than to the subtraction. Okay, so on the plus side right now we have k plus 6, and on the subtraction side we have deduction of 2. And now I can utilize the zero product property, setting each of the factors to 0. And for k plus 6, okay, if we have that k plus 6 is equal to 0, okay, we're going to have that k is equal to negative 6. And if k minus 2 is equal to 0, and we have that k is equal to 2. Okay, now we have 2 apparent solutions, and it might be that both will work out, or it might be that only one of them will work out, or it might be that we are not going to have any solution. And so for what we have in this case, if we go back to the original equation, say if I check negative 6 for k. Okay, so if I plug in negative 6 for k, so you have negative 6 plus 7. Negative 6 plus 7 is 1. So you have the square root of 1 We've got minus the square root. Okay, now 3 minus negative 6 translates to 3 plus 6, so this is going to be 9. And the square root of 1 reduces to only 1, and then we have subtraction. Square root of 9 is going to be a 3. And for the activity on the left, we have 1 minus 3, which will be negative 2. And guess what we have to the right is 2. And negative 2 and 2 do not equal to each other, and so negative 6 does not meet the bill qualifying as a solution. Now, so negative 6 is out of the running. Now for k equal to 2, if I check out this value, okay, so plugging in 2 for k. Alright, so you have 2 plus 7 is going to be 9. So you have the square root of 9. We have minus, okay, the square root, okay, and 3 minus k is going to be 3 minus 2, which is 1. We have is equal to 2, and the square root of 9 is at 3. We have minus, and have the square root of 1 again is at 1. 3 minus 1 is 2, and 2 is equal to 2, so this is going to check out, and so 2 meets the requirement of everything that is required for it to be a solution. So for this equation with two radical terms, okay, there's only one solution, and that is at k is equal to 2. Now, for what we have also in working with equations, and the next item, okay, up, okay, this is going to be kind of a early visit part of what we will be looking at in the next chapter, okay? And this is just interchanging expressions for what we have in the variables x and y. And for what we have in number 91, okay, so we have like solving an equation for a specified variable, and we have in this one looking at 4x minus 3y is equal to 6, and you're looking at expressing or solving for y. And we have, right now we have the y term at negative 3y, and in creating the pathway to get this in terms of y equals, okay, right now we have a couple of obstacles. One is the term 4x, and the other we have with the coefficient negative 3. And I can proceed by at least moving the 4x over. Okay, so upon subtracting, okay, so the left hand side, okay, we're going to have at negative 3y, and you can express what we have as negative 3y is equal to 6 minus 4x, or negative 4x plus 6. And looking at solving for y, okay, I took care of the 4x. Now I'm going to take care of negative 3 upon dividing the terms by negative 3. And upon doing so, negative 3y over negative 3, this will become y. And for negative 4x over negative 3, a negative over a negative becomes a positive. And 6 over negative 3 becomes negative 2. And this form is going to be what is regarded as the slope-intercept form of a linear equation. Okay, so we have y is equal to 4/3 of x minus 2. All right, now also looking at solving an equation for a specified variable. Okay, and we have in the case of number 96, okay, now we've got the letters A, B, and C involved. And this problem is somewhat tricky because we have fractions that are in the mix. And right now we have the reciprocal of A is equal to the sum of the reciprocals of B and C. And right now we have 1 over A equal to 1 over B plus 1 over C. And we're looking at solving for B. In other words, we're getting this in terms of B equals, but right now we have B as a denominator in the second fraction of this equation. And for what we have here, okay, one pathway we can create, okay, is to just go ahead and get rid of the fractions. That is the denominator, all the denominators throughout. Now, since we have an equation, we can clear out the fractions, multiplying all the ratios out by the least common denominator, okay, which would be ABC, and multiplying these terms out by the least common denominator. Okay, so you have, first of all, we have ABC multiplying 1 over A, and here I can get the A's to vanish. So we have B times C on the left, and with the terms on the right. Okay, so you have ABC multiplying 1 over B so ABC multiplying 1 over B. I'll just move this over here. Okay, so we can get the B's to vanish. Okay, so I have A times C, and distributing ABC over 1 over C. And looking at it through the lens of cross multiplying, we have the C's will go out. And so now we have BC is equal to A times C plus A times B. And I'm looking at solving for B and trying to get B by itself and as a single entity. But right now I have two terms consisting of the variable B. So what I can do at this stage, so I have taken care of the fractions, just canceling out the denominators, having utilized the least common denominator. And now for BC is equal to AC plus AB, I can join together the terms in B. So I have BC by itself, and I can move AB upon subtracting. Okay, so I have BC minus AB is equal to AC. All right, and I still have the obstacle, okay, with a couple of B terms. What I can do to make this as a single entity in B, notice that between BC and the negative of AB, we'll have a common factor with B. And if I factor out B from BC minus AB, and we'll have B times the quantity of C minus A. And looking at isolating what we have for B, I can just divide both sides by C minus A. So we have that B is equal to AC all over C minus A. Okay, so that would be the result for what we have in number 96. Now, in looking at what we have in the realm of equations, okay, where we might have various types of solutions in the mix, and 105, okay, presents a case Yes.
That last one, when you get to the point where it says BC equals AC plus AB, why couldn't you just divide both sides by C?
Okay, if I did that, I'm still looking at solving for b, because if I divide it by c, it would be like I'll show you. If you did that, I was going to move to the side here. If I divide it by c, okay, like the c's to go out here, and I have like b is equal to a plus ab over c. I still have this b term to exist.
Oh.
Yeah, and I'll show you this because I had somebody ask me a question pretty similar to that one, and if I took away ab over c, yes, I have b minus ab over c, and I have is equal to a, and guess what? If I factored out b, I have like 1 minus a over c is equal to a, and getting b by itself, if I divide it, let's say you have a all over 1 minus a over c, I would have a complex fraction, not as in complex fraction in the letter I, but just where you have like a ratio within a fraction. And if I looked at getting rid of the excessive presence of any denominator, like in the case c, and I just multiplied by 1 in the form of c over itself just to clear out that denominator, what would happen here is that, okay, we have a times c is ac, and if I multiply 1 minus a over c by c, got c times 1 is c, and negative ac over c, c's will cancel out. You have like ac over c minus a. It is still solvable, but you would create a pathway where you would be undoing a complex fraction. But it's still workable. It would just take more steps.
Yeah, that seems way more complicated.
Yeah. Okay. Yeah. Yeah, and want to minimize those situations. Okay, now for what we have in the case of 105, okay, now we have what's going to be a quadratic equation in the letter x, and right now we have x times, okay, the quantity of x minus 4 is equal to negative 9. And looking at distributing, okay, so I have x squared minus 4x is equal to negative 9. So I have a quadratic equation that is not yet set up, okay, in standard form. And I can just go ahead and add 9 to both ends. So we have x squared minus 4x plus 9 is equal to 0. Now here I have a trinomial, but it is not one that I can factor into real integer coefficients. Like there are no integer factors of 9 that will add up to negative 4. So as a recourse, okay, if there are to be any solutions, okay, I can utilize, okay, the quadratic formula. So for what we have here, okay, so you got like x squared, or you can read as 1x squared. Okay, so you have a is equal to 1. And for what we have next, okay, for negative 4x, okay, so I have b is equal to negative 4. Then we have that c is equal to 9. Okay, so we have for x, okay, with the quadratic formula. So we have x equal to negative b plus or minus And we have the square root b squared minus 4ac all over 2a. And so for what we have at the substitution stage, okay, so for negative b, we have the opposite sign of negative 4. Yeah, plus or minus, okay, the square root. Okay, so you got b squared is the square of negative 4. You got minus 4 times 1 times 9. And you have all over 2a, because you have 2 times 1. Now, for the radical, okay, so I have the square root. Okay, now the square of negative 4. Well, negative 4 times itself. Okay, this will be 16. Negative 4 times 1 is negative 4. In turn, negative 4 times 9 is negative 36. 16 minus 36 will be negative 20. And here we have a complex number. They have square root of negative 20. Okay, now we can just go ahead and factor out the letter I. Now 20 is not a perfect square, but it is the multiple of a perfect square that is greater than 1. And that perfect square is going to be at 4. And in the reduction, okay, so you have the square root of 4 is 2. Then we have times the square root of 5. Then we have I. Again, I is going to be outside the radical, and you can also write that as 2i times the square root of 5. So just looking at taking what we have in the process. Okay, so you have the opposite sign of negative 4 is 4. You see, have 4 plus or minus. And again, for the radical, we have 2 times the square root of 5i. We have all over 2. Again, all 3 terms have an even valued leading coefficient. So we have 4 over 2 is 2. And for the I term, positive and negative, the 2's are going to cancel, so we're going to have 2 plus or minus the square root of 5. We have times I. And just looking at what we have and itemizing, okay, so we can see we have 2 plus the square root of 5i. And also we have, separately, we have 2 minus the square root of 5. We have multiplied by I. And again, I remains outside the radical. Yes?
Do all 3, for you to be able to reduce that, do all 3 of those numbers have to be, like, what if it was 4 plus or minus 3? Square root of 5i over 2.
Okay.
You couldn't reduce that, right?
What would have happened? Let's see. Yeah, if you had like, if you didn't have unanimously even valued leading coefficients. Say if we had something like 4 plus or minus. Okay, you have 3 times the square root of 5i over 2. Okay, if you had to do it like putting in standard form, let's say, if you didn't, you could just, I know what you're saying. Say that you have 4, let me put it this way. Okay, if it's not asking to put it into standard form, you have like 4 plus 3 times the square root of 5 times I over 2. And 4 minus 3 times the square root of 5 times I all over 2. But now, if it doesn't ask for standard form, that would suffice. But I'm just going to mention. I'm just waiting for things to stabilize here. I don't know why the equipment is so jumpy. But in the standard form, if it asks for the standard form, like the a plus bi form, yeah, so like your A, you will start out with 4 halves. And 4 halves minus. And you have 3 times the square root of 5i over 2 and exclamation case. So for your standard form, you have like 4 halves is going to be 2. You have plus 3 times the square root of 5 over 2, okay, times I, and you have like 2 minus. Same thing here. 3 times the square root of 5 over 2, okay, where that ratio is also multiplied by I. But if it doesn't ask for the standard form, that part is okay. But if it were to ask for the standard form, you would separate where your A value is going to be at 2 and your BI terms would be like positive or negative 3 square root of 5 over 2 times I.
Thank you.
All right. Now, in the case of what we have for equations, okay, that are not just quadratic, but quadratic in form, and looking at what we have for 106. Okay, now we have an equation in the variable d, and we're looking at solving for d, okay, whereupon we have 6 times d to the 2/3 minus 7 times d to the 1/3, okay, and we have minus 3 is equal to 0. Alright, so here we have an equation that is quadratic in form because the higher degree in d is double the degree of the lower power appearance of d. Okay, you have 2/3 to 1/3 is a 2-to-1 ratio. So we say we have this equation is going to be quadratic in d to the 1/3. Okay, and just sort of stepping to the side here, okay, in terms of creating a pathway for factoring. Okay, now we're not dealing with the traditional type of quadratic equation, but just if you think of a quadratic expression to factor, like you have 6x squared minus 7x minus 3, and you looked at factoring by grouping. Okay, so you have like your leading coefficients. Okay, you have 6, or to say the first and last coefficients, we have 6 and negative 3. And 6 times negative 3 is negative 18. Now one of the factors of negative 18 that will add up to negative 7. Well, those numbers will be negative 9 and 2. Again, so we would have negative 9 times 2 is equal to negative 18 and negative 9 plus 2, okay, is equal to negative 7. So this is the combination of coefficients that we seek. Okay, so, and upon splitting up, okay, so we can say we have 6x squared minus 9x, and we have plus 2x minus 3. Now looking at grouping case, you have 6x squared minus 9x, and you have plus the quantity of 2x minus 3. and drawing out the greatest common factors, so between 6x squared and negative 9x. Okay, so we got variable x in common, and 3 is the highest number that will go into 6 and 9. So the greatest common factor is going to be 3x. And we have times the quantity of 2x minus 3. We got plus, and the greatest common factor of 2x and negative 3 is just going to be 1. And we also have times the quantity of 2x minus 3. So for the breakdown, okay, so we got the shared factor with 2x minus 3, and combining the outside terms in operation, that is with the addition clustering together the respective greatest common factors. Okay, we have 3x plus 1 as the other factor of that trinomial. Okay, now in terms of how this plays out for what we have in this particular equation. Okay, so I'm not working with x squared and x, but d to the 2/3 and d to the 1/3. And so just drawing a parallel. Okay, now we got the same coefficients. And just the 6x squared factors out to 2x and 3x. We can say 6d to the 2/3 will factor out not to 2d or 2x, but 2d to the 1/3. And 3d to the 1/3, and we have minus 3. And we have 3d to the 1/3 plus 1. And we have this equal to 0. Okay, so this is what we have here. Okay, and just looking at putting forth, okay, the zero product property. Okay, we can itemize the terms. So you have 2d to the 1/3 minus 3 is equal to 0. And we have 3d to the 1/3. Okay, we have followed by the addition of 1 is equal to 0. And looking at isolating 2d to the 1/3. Okay, so if I add 3 to both sides, okay, so I'm going to have, we have 2d to the 1/3 to the 1/3 is equal to 3. And upon dividing by 2, just to get the d to the 1/3 by itself, so d to the 1/3 is equal to 3/2, and just converting from an expression with a non-integer exponent to its radical counterpart. So d to the 1/3 is going to be the cubic root of d. So the cubic root of d is equal to 3/2. Then we have, in cubing both sides, so we have for one solution of d, okay, this will come out, okay, 3 cubed is 27, and 2 cubed is going to be 8, so one solution will be 27/8. And for the other, okay, for 3d to the 1/3 plus 1 is equal to 0. So if I isolate, so just taking 1 away from both ends, okay, so I'm going to have 3 times d to the 1/3 okay, is equal to -1. And with division by 3, okay, so I have d to the 1/3 is equal to -1/3. And so for d to the 1/3, okay, so this will be the cubic root of d. we have is equal to negative 1/3. Okay, and let me just mention, now we're dealing with an odd root radical. If I had an even root, like the square root or the fourth root, let's say, there would be no solution for, in those scenarios, the principal square root rule would have been violated. But with odd roots, the principal square root rule does not apply. And so, looking at solving for D, once again, I can cube both sides. So for the cubic root of D cubed, okay, that's going to go to D. And negative 1/3 cubed, okay, have negative 1/3 times itself. And so that is going to end up at minus 127. Okay, so you have 27/8 and negative 127. Okay, all right. Now, in the crossover, okay, to what we have with inequalities, okay, now we have as well as absolute value, and we have from the group, and we have from page 115 in the case of number 130. Okay, we have for part A, okay, now we're looking at solving for W. And here we have the absolute value equation, okay, whereupon we have the absolute value of W plus 2 followed by the addition of 1 is equal to 6. Okay, and again, I want to get the absolute value term by itself. And so, for what we have here, I can deduct 1 from both sides. Okay, so I'm going to have the absolute value of W plus 2 is equal to 5. Okay. And again, so this is like a scenario that if K is a non-negative value, and we have that the absolute value of X is equal to K, then X is equal to positive or negative K. Well, here we have X to be represented by W plus 2, and K is represented by 5, okay, which is non-negative. So once I take out the absolute value signs, we have that W plus 2 is equal to plus or minus 5. And so for what we're going to have in this case, all right, is that looking at isolating what we have here. So we got for W plus 2 equal to plus or minus 5. Okay, so we have on the one end okay, so W plus 2 is equal to negative 5. Again, we have the other possibility. We have that W plus 2 is equal to 5. And in both of these, okay, so you have taken 2 away from both sides. Okay, and so for W plus 2 equal to negative 5, okay, so we're going to have that W is equal to negative 7. For W plus 2 is equal to 5, okay, we're going to have that W is equal to 3. And so here we're going to have that W is equal to negative 7 and positive 3. Okay, now for what we have in the second part, okay, now we have the absolute value of W plus 2, okay, followed by the addition of 1 is less than 6. Okay. And just a bit of history to repeat. Okay, instead of an equation, we have a less than inequality statement, but I got the same terms, and I'm going to isolate what I have in W upon subtracting 1 at both ends. So once again, we have W, the absolute value of W plus 2 on one side and 5 on the other. Okay, so I had the absolute value of W plus 2 is less than 5. And if the direction is where I have the inequality to be less than or equal to, upon removal of the absolute value signs, okay, there'll be a compound inequality formed where W plus 2 in this case is going to be situated with where it lies between negative and positive 5. So we're going to have negative 5 is less than W plus 2, which in turn is going to be less than 5. And for getting W by itself, okay, so we're going to subtract 2 from all portions that make up this compound inequality. Okay, so upon subtracting 2, we now have negative 5 minus 2 is negative 7. Negative 7 is less than W, and W in turn is going to be less than 3. So for what we have, just looking at the picture, think of a number line. We got negative 7 and 3, and neither value is going to have a close point, so you just have open circles, and connecting, okay, we're going to have a line segment. And so for the interval solution, okay, so you have between negative 7 and 3, but not including either of these values. Okay, so for the grouping, we have parentheses to enclose, and then we have in the other inequality scenario, okay, so we have in part C. Okay, so we got the absolute value of W plus 2, followed by the addition of 1, and we have is greater than or equal to 6. And looking at taking 1 away from both sides, we have that the absolute value of W plus 2 is going to be greater than or equal to 5. Okay, so again, whenever the inequality in the absolute value, okay, is said to be less than or equal to, you had the formation of a compound inequality. However, if you have greater than or equal to, you're going to have separate inequality statements where you have the expression upon removing the absolute value bars will be said to be, in this case, less than or equal to the negative of k. And we have at the other end, we have the same expression will be said to be greater than or equal to what represents positive k. And so for W plus 2, if we put these inequalities in terms of W, so we have upon taking 2 away from both sides, okay, so we have that W is less than or equal to negative 7. Or it could be that W is greater than or equal to 3. And just visualizing what we have here. Okay, okay, so we have so we got negative 7 and 3. And we have W is less than or equal to negative 7, so with the equal sign, okay, negative 7 is included, W is less than, so we're going to have activity to the left. So we have array going to the left, and for w is greater than or equal to 3. So we have a close point on 3 thanks to the equal sign, and the rest of the values are going to be greater than. And so we have array that is going to be going out to the right. Okay. And so we have just for the extremes, just have going to the left out toward negative infinity, and out to the right towards positive infinity. And for what we have in the case of the interval solution, okay, so you're going to have again from negative infinity approaching and including -7. Also have another for the other interval section, so we're going from and including 3, and we have going out to infinity. So that would be the interval solution for what we have in the case of part C. All right, and now just okay, from what's going to be in the next portion. Okay, and this will be the introductory topic, okay, to chapter 1, and we have in the case of functions, and we've already dealt with those in various capacities, but for the official definition of what we have concerning functions, okay, now a function is going to be a mathematical relation okay, where, okay, now there are various types of coordinate systems you could be dealing with, but for all intents and purposes, we're going to be dealing with predominantly, okay, the XY coordinate system. So we have for a function, you have a mathematical relation where in the XY coordinate system, for each x value, okay, there's going to be one and only one corresponding y value. And I'll just stress this, okay, so we have here for each x value, okay, there is one and only one corresponding y value. And just kind of providing a little bit of a backdrop, okay. For the XY coordinate system, okay, each point is identified as an ordered pair. And all ordered pairs are of the form XY. and just kind of separate. Okay, for each x value, there is one and only one corresponding y value. Okay, now in terms of the characteristics, okay, now x, this is going to be regarded as the independent or input variable. And for what we have in the case of y, okay, that's going to be the dependent, or also what is referred to as the output variable. And for what we have as examples of functions, they could be in equations, but for at least for introductory purposes, okay, if we look at it, okay, through taking what we have as sets of ordered pairs. So like first case, all right, so we have, let's say we have 0, 2, as well as 3, 5, and also -1, 9. Okay. And so for what we have here for functions, again, for each x value, there's going to be only one corresponding y value. So you got your x values at 0, 3, and -1. So you have 0 is uniquely paired with 2, 3 uniquely paired with 5, and -1 is only joined with 9. And now, just for the characteristics, now you'll be running into the term domain quite a bit. And in the case of the domain is going to be making reference to the set of x values that define the function. And the domain, okay, so you have the set of the numbers. Okay, so you have 0, 3, and -1, and as long as you had those three elements, you got the right values, okay, for the domain. And you can put those in most any order. So you have 0, 3, -1. And if you want to put this in numerical order, and I know that the author likes to, or as well as the authors of many other books like to put the domain like in increasing numerical order. But if you have like 3, 0, -1, 3, -1, 0, or 0, -1, 3, you still have all the values that make up the domain. Now, for the y values, okay, this will be what is going to be regarded as the range. And the range will be the set of y values. And for the range, okay, so you got the y values, so you have 2, 5, and 9. Now, another case of a function. You see we have -1, 1. You see we have 0, 5. As well as 3, 9. As well as 4 and -6. Okay, this is also going to be a function, okay, because your x values have -1 paired up only with 1, 0 with 5, 3 with 9, and 4 with -6. Okay, and looking at identifying the domain. Okay, so you got the x value, so you have -1, 0, 3, and 4. And as for the range, okay, we'll have 1, 5, 9, and -6. And again, you can just put down the numbers in the order that you see them. Again, if you were to care to rearrange, just putting in order from smallest to largest. So this would be -6, 1, 5, and 9. Okay, so again, for the XY coordinate system, a function is going to be where for each x value there will be only one corresponding y value. And just kind of a quick set of thought experiments, okay, in terms of whether we have a function or not. Now, say we have sets of ordered pairs. Say -1, 1, 3, 4, and 5, 7. And say we have another arrangement. Okay, say we have -1, 1, 3, 4, (5, 7), and say we have 3, -8. Now say we have also in the mix, okay, say we have 0, 1, 1, 1, and 2, 1, and finally we'll say that we have, kind of flipping the x and the y values from the third set. We have 1, 0, 1, 1, and 1, 2. Okay. All right. So we have for the first set of order pairs whether we have a function or not. So you'll be looking at the x value. So you have -1 appears only one time, so it's uniquely paired up with 1, and 3 it appears once as an x value where it is uniquely paired up with 4, and 5 appears only one time, and that is uniquely paired up with 7. Okay. So for this case, all right, the answer is yes. And just a quick mention, so you have for the domain, okay, you're looking at -1, 3, and 5. Now for what we have in the case of the range, okay, so you have 1, 4, and 7. Now for the next scenario, okay, so you got the first 3 ordered pairs repeating. Now we have the addition of 3 and -8. Okay, so again, -1 is uniquely paired up with 1, 5 is uniquely paired with 7. But in the case of 3, this one appears twice, and 3 is no longer uniquely paired with 4, because after it shows up again, if I had it like another 3, 4, it would still be a function on the basis that 3 would still be uniquely paired up with 4. But in this particular case, because 3 shows up again, but it's paired up with a different number, so you got same x, and a different y, so we have in consequence. Okay, second case is where we have a set of order pairs that will not be a function. Now for what we have in the third scenario, okay, and so we got 0, 1, 1, 1, and 2, 1. Okay. This one might be a bit tricky, but again, each x value must be uniquely paired with a y value. So again, you have 0 is its own x value, and it's paired up only with 1. Guess what? Okay, 1 is its own x value, and it is paired up only with 1. And 2 is uniquely paired with 1. So you can have repeating y values, but as long as you have x values that do not repeat with a different y value, it is going to be a function. So you have, in the case of the domain, okay, you got your x values, okay, which we will have at 0, 1, and 2. Now, so what we have in the case of the range, okay, so you had the only y value to be at 1, so the range is just going to be 1, and you don't have to repeat that number. Okay, so just one, putting it down one time in spite of repeating. Okay, so that is going to take care of that. And now for what we have in the final instance, okay, so I just switched the order of the x and y values. Now let me mention this, okay, a function that has its x and y values switched, and the switching is going to also form like another function. That original function will be regarded as a one-to-one function. That's a future topic we'll be looking into. And if you notice, you have a 1, 0, 1, 1, 1, 2. Guess what? We have for these. We've got same x and different y values. So we have this last case, okay, that is not going to be a function.